All right. Good afternoon, everyone. Now we are going to start our third LCTS session. We have two full papers talking about the scheduling and three WIP work in progress papers today. So the very first talk is from Alexandre Honorat. He got his PhD from Inria, France, and he's interested in working on the data flow graphs. And currently, he is a postdoc researcher at Inria Research Institute in Grenoble, France. All right, let's welcome the speaker.
Well, thank you for the introduction. So I will present you this work about sequential scheduling of data flow graphs for memory peak minimization that we have done with Pascal Fradet and Alain Girault, my two postdoc supervisors at Inria. So our motivation for this work comes from two facts. First, modern computing systems still have a limited memory. This is especially the case of embedded systems. And second, modern applications use an increasing amount of data. And this is especially the case of neural networks during their training phase. So our goal is to limit the memory used by data flow applications in order to meet these two constraints. And we consider specifically task graphs and synchronous data flow graphs. So as an input, we consider directed acyclic graph, which has memory cost on the nodes and edge attributes. And as an output, we want to compute a sequential schedule having the minimal memory peak, that is, the maximal amount of live memory during the execution. But this problem is quite difficult to solve. In fact, if you want to solve it naively, you have to test all the schedules, and their number is exponential. It's actually NP-complete, and it's a variation of the Peeble game for register allocation. So here is an example of a task graph with memory cost attributes on edges. And you can notice that the amount of memory on both sides of all edges is the same. So here, node E consumes 4 data tokens and produces 1 data token when it's executed. And we have 3 schedules to test in this case. So if we interleave node E between C and D, then the peak will be 13. I will not detail the computation, but if we move it between B and C, then it's only 11, and actually it's even only 10 when we execute node E between A and B. Here we have an intuition, which is that the node E consumes more data tokens than it produces. So we want to execute it as soon as possible. So to solve this problem, we have developed a small set of peak-preserving graph transformations. This is our main contribution. So why graph transformations? Because, as I said, if we want to compute the solution naively, we have to test all the schedules. So what we want to do is to remove this number to reduce this number of schedules. And so we will do it by clustering nodes and sequentialize them, which will remove nodes or remove parallel paths. And by peak-preserving transformations, we mean that we want to ensure that our transformation preserve a schedule with the minimal memory peak in the transformed graph. So again, as an input, we consider a graph which has production and consumption rates per edge. And in this case, node A consumes S tokens and produces R tokens, which are actually the sum over all the incoming and outgoing edges. But internally, we will consider another representation of the input graph, which has only peak and impact attributes per node, not anymore per edge. The peak can be any integer, positive integer, and in the produce before consume model, it's actually the number of produced tokens R. And the impact corresponds to the intuition we had before, so it's just the difference between R and S, production less, minus consumption. So here is the first example again. The input graph on top and below the internal representation of this graph with only attributes on the nodes. The peak and the impact actually have multiple good properties. And the first one is that we can use them not only for nodes, but also for sequence of nodes. So the operation, PI, gives the impact of the sequence of two nodes, A and B. So if we consider the subschedule A, then B. The impact is simply the sum, and the peak is the maximum of first peak, and then a maximum of first impact plus second peak. The good property of operation PI is that it's associative on both nodes and sequence of nodes. This gives us the direct application that is linear time computation of the memory peak of any schedule. And here is the first application. So it's our first transformation rule, peak preserving transformation rule on the internal graph. This is a simple transitive reduction that you most probably all of you know. So here the edge in red between node B and D can simply be removed because it does not carry any information. All attributes are on nodes. And most importantly, this does not change the set of all possible schedules. So we can remove it, and this simplifies the graph. The simplification is a good thing for our main transformation rules, which are the following ones. So we have 4 rules, 2 for clustering and 2 for sequentialization. And in both cases, they are symmetrical if we consider the predecessor nodes or the successor nodes. So I will explain only the rule C1 and S1. So for clustering, here we want to ensure that for the 2 nodes in sequence A then B, if we consider any extra node S, which can be interleaved between A and B, then the peak of this schedule, the memory peak of this schedule, will always be higher than the peak of not interleaving S and executing it before. And we have proven some conditions which ensure this property. So there is a topological part for this condition, a single successor for node A, and an arithmetical part on the impact and the peak of both nodes A and B, but not S. If the condition is met, then we can cluster the 2 nodes A and B, and the new node will actually store the schedule sequence A then B. And this reduces the number of nodes as we wanted. Then the sequentialization rule is quite similar for the intuition. We also consider an extra node S that we want to interleave in the schedule of A and B. Here, A and B have a common predecessor. The topological condition will be slightly different. Then it's an inclusion of the predecessor set and the ancestor sets that are predecessors in the transitive closure. And the arithmetical conditions also are on the impact and the peak on the involved nodes, only A and B. Again, if the condition is met, we can apply the transformation. And here we add the edge in red between node A and B. So this reduces the number of parallel paths as expected. So we have seen in total 5 transformations, the transitive reduction and the 2 clustering and sequentialization rule. We can combine them in a single algorithm, and which will apply all the rules until none applies. We start by the clustering rule because it's the cheapest one to check. And the most expensive one is the transitive reduction, cubic time, so the complexity of the whole algorithm is quartic time. We also have proven a few theoretical results on both the transformations and the algorithm. First, any compressed graph always admits at least one schedule having the minimal memory peak once we have transformed it with our rules. And a direct application is that if the graph is compressed to a single node, then it contains the minimal, this node contains the schedule giving the minimal peak. It's one of the schedule giving the minimal peak. Next to our result is about a specific class of task graphs, the series parallel task graph, which we always compress to a single node. But there are cases where the compression algorithm does not compress the graph up to a single node. So in this case, we come back to the first idea of exploring all the schedules. So we have implemented a dedicated branch and bound search, which is our second contribution. So we apply it only if the graph is not compressed to one node, and it follows the generic idea of a branch and bound. So we backtrack each time we encounter a schedule, a new schedule, which has a memory peak higher than the previous better known one. Our contributions actually are on two optimizations for the branch and bound. First, a longer backtrack up to the previous peak instead of the previous node, and a smaller ready list if the next node has a negative impact, which corresponds to node E in the first example. So this algorithm is always optimal for instance size up to 50 nodes, but then it explodes if we have more than 100 nodes. It's still an NP-complete problem. But we can set a timeout, and we will always have at least one solution. We did the last contribution, which is an extension of those results to synchronous DataFlow graphs. So synchronous DataFlow graphs are an extension of task graph, which has unbalanced send and receive amount of data as weights on the edges. So here, for example, node A produces two data tokens, and node B consumes only one. So we have to execute node B twice so that we consume all the data which are produced. And those SDF graphs can be expanded to task graph as we consider in the first part. But there is a problem. The expansion into the regular task graph can explode in size. This is especially the case when the weights on edges are relative prime numbers. So as the last contribution, we have developed a suboptimal partial expansion of the SDF graph, and we give detail in the paper. I will not present it. I will instead present a few experimental results. So we have considered a small benchmark of SDF applications that we have fully expanded to a task graph, and especially the satellite and QMF applications. And in this case, we always outperform state of the art. And actually, all those graphs are compressed to a single node, so we ensure to compute the minimal peak. In only one case, another work finds the optimal peak, but without the guarantee of optimality. So, as a conclusion, we have developed a few peak-preserving transformations, which can be applied also optimally to some subclass of DataFlow graphs, especially trees and SPNAG. And if the transformations are not working up to a single node, then we have developed a dedicated branch and bound algorithm. As future work, we would like to consider parallel scheduling, or maybe try to apply our peak preserving transformation to other problems. So I leave you with the references of the most related work, and I'm ready for questions.
All right, Q&A, questions from audience? In the meantime, let me ask, you talk about the optimality, I mean, the minimal guarantee. Can you also talk about the time, you also talk about the time complexity. How about the space overhead? Do you need any additional space to guarantee this minimality?
You mean in our algorithm?
Yes.
The space complexity of the transformations is not so high, even if we have to compute transitive closure, but we can compute it partially. But at worst, the transitive closure will be quadratic. And for the branch and bound, it depends. The most simple implementation is maybe linear, I think. But we have developed, it's not presented in the paper, but we have another implementation which is quite more demanding in size, in space. Okay. Yes.
All right. Any more question? All right, let's thank the speaker again.